Howdy. Today, at 3rd of March, 3/3/23, we have another Parzen lecture here. And let me say a few words about the Parzen lectures, and then Val will introduce our speaker for today. The Parzen Prize is named for Emmanuel Parzen, a long-time distinguished professor of statistics at Texas A&M, who passed away on February 6, 2016. It is established through the Texas A&M Foundation, and first award was given in 1994 to recognize Parzen's 65th birthday. I will give you a short list of Parzen awardees. These are all distinguished statisticians: Grace Schwab, Donald Rubin, Bradley Efron, C.R. Rao, David Brillinger, Jerome Friedman, Alan Gelfand, Nancy Ray, Marvin Zellen, Roger Conker, Adrian Raftery, Trevor Hasty, Bill Cleveland, Bin Yu, and this year we had also Herman Chernow. In year 2020, because of COVID, we did not have awards, but Herman Chernow, who was supposed to be in 2020, is awarded this year. And today we have Peter McCullagh, who is going to be introduced by Paul. Let me say a few more words about Emmanuel Parzen. He joined Texas A&M in 1978 and retired in 2009 as Distinguished Professor Emeritus of Statistics, but remained active in his research. In 1994, he was awarded Samuel S. Wilkes Memorial Medal of the American Statistical Association for outstanding research in time series analysis, especially for his innovative introduction of reproducing kernel spaces, spectral analysis, and spectrum smoothing, for pioneering contributions in quantile and density quantile functions and estimation, for unusually successful and influential textbooks in probability and stochastic processes, and for excellent and enthusiastic teaching and dissemination of statistical knowledge, and for commitment to service on society councils, government advisory committees, and editorial boards. In 2005, Parzen received the Gottfried Notter Award for lifetime outstanding achievements and contributions in the field of non-parametric statistics, both in research and teaching. This is an award which is also called Carol Parzen. It is Emmanuel and Carol. Carol was Emmanuel's wife. She earned her Master's of Science in Adult Extension Education from Texas A&M and was retired from Texas A&M Main School of Business. She was served as Assistant Director for CBA Fellows Program. The Parzens were married in 1959 and had 2 children, Sarah, who is now in Boca Raton, and Michael, who is Senior Lecturer of Business Administration at Harvard University Business School. So, without further ado, I will ask Val to introduce the speaker today.
So it's a real pleasure for me to introduce Peter this afternoon, or I guess it's still morning. I'm going to go through a number of Peter's accomplishments, but before I did that, I thought I would start with the notable failure. So Peter was one of my first instructors when I was at the University of Chicago, taught generalized linear models. So this was a really fantastic course. It, despite the outcome for me, it served many other students very well. And I think together with my eventual advisor, Wing Wong, it turned out that Peter and Wing just were the most influential people in my career, I think, in terms of my perspective on statistics and data analysis. So before I get to Peter's contributions, I would just like to say thank you, Peter, for all you've done for me. Peter performed his undergraduate studies at the University of Birmingham and his PhD studies at Imperial College under the direction of David Cox and Anthony Atkinson. He's made many contributions to statistics and he's received many awards. I'm just going to list a few. With John Nelder, Peter is co-author of the seminal text Generalized Linear Models, which I think everyone is familiar with. He pioneered the generalized linear model extensions to ordinal regression models, proportional hazards models. The monograph, generalized linear models, has now been cited over 20,000 times. Peter is a fellow of the Royal Statistical, or the Royal Society, as well as the Royal Statistical Society. He's a fellow of the American Academy of Arts and Sciences. He's the recipient of the Royal Statistical Society's Guy Medal in bronze and in silver. He's the recipient of the inaugural Carl Pearson Prize of the International Statistical Institute for the monograph Generalized Linear Models. And most recently, he's authored 10 projects in applied statistics, which again emphasizes basic principles of statistical analyses, the importance of making these analyses relevant to the consumers and the clients, and really taking a look at some of the underlying assumptions of models that I think we often fit without really thinking very much about. So it's my pleasure to welcome Peter to Texas A&M. Peter,
well, thank you. Am I supposed to start with howdy? Howdy. Okay. Well, this is a great honor to be asked to present the Emmanuel Parzen lecture. I think I've met Manny Parzen only once. He showed up completely without appointment in my office one day. His son Michael was teaching in the business school at the University of Chicago, and I guess Manny was visiting. I don't remember, must have been sometime in the 90s probably. And just knocked on my door and said hi. And of course I recognized who it was immediately. From photographs, I've probably seen him give lectures here and there. So I recognized somebody, introduced themselves. Hi, I'm Manny Parzen. I don't want to take up too much of your time, but he came in and sat down, and we had a nice long chat for half an hour or so. And anyway, that's the basic. He seemed like a very pleasant fellow and nice, warm character, and I had only the warmest feelings about him. So that's basically my connection with Manny Parzen. Not much, but that's it. So when I was asked to present this lecture, of course I was at that time trying to finish up this book, which is just appeared in time for the Parzen lecture. It's just come out in the last month. And I thought, well, maybe I should talk something methodological about what I was working on, what I am still working on, which has to do with sparsity. But somehow that didn't quite develop. And I thought, well, I'll try to be a bit more adventurous and I'll talk about some of the material in this book, and maybe go through a couple of the examples. But as I started preparing these examples, well, they turned out to be longer and more complicated than I had remembered. And by the time I had prepared all the slides, there were something like 60 or 70 of them. So I thought I cut it down to one, then from 2 to 1. So the initial title was 2 topics in applied statistics, but it's now down to 1. And this one is on this particular topic. It's from evolutionary genetics. So this is partly a methodological talk, but it's also very specific to this particular issue that arises in genetics, which has to do with the issue of how species are formed. And basically the sort of the prevailing wisdom in genetics is that you have got population, and somehow they become geographically isolated. You split them up into 2, they're initially identical and they can interbreed and so on. And but after many subsequent generations, sufficient mutations build up in one that are different from those that build up in the other group, and eventually barriers to interbreeding come into play. So let's right. So this is, well, we'll talk about it. So this is the thought I'd put in a plug for the book right at the beginning. So there it is. And just so that you get an idea of the flavor of the book, the first 10 chapters are on specific application. Now, these are all applications in scientific work. And so that you know exactly what I mean when I use various terms, I have handed out a sheet of paper. And these are not meant as definitions. These are orthodox definitions, I suppose, but they are mostly orthodox definitions, but they're definitions in the sense that I will use the words today. So I'm going to use the word covariate in a very, for example, in a sense that's much narrower than many people would use the word. So bear that in mind. So now of these first 10 chapters, 2 of them, the ones in blue there, are associated with genetics and specifically with speciation. One of them in fruit flies and the other in lice. Many of these sorts of experiments sort of make your skin crawl a little bit when you think about them, and then the lice data is one of those. And the more you know about the details of the experimentation, the more your skin will crawl. So be aware of that. I think those are the only 2 genetic. Actually, there are 2. Chapter 3 has 2 different projects, both involving Drosophila. Chapter 5 has only 1. So the title 10 projects isn't to be taken too literally. That's 10 chapters. Okay, so this is an experiment to do with the evolution, or the differential evolution, I should say, of louse size on pigeons, and it's based on the claims in this paper, and I'm not going to read out the authors. There are, I think, 10 or 11 of them. And you can see from the title, Rapid Experimental Evolution of Reproductive Isolation from a Single Natural Population. So you can understand what, in some sense, what it's all about. And I'll give you details of the experimental setup in a moment. It's actually based on a class project by a student in a class that I taught a few years ago, one of the last classes I taught in Chicago, and it was a class specifically on projects of this sort. And it's, I suppose, my favorite of the chapters in the book, my favorite of these projects. Okay, so what is the whole thing about? Well, it's easy enough to describe the experimental setup, which begins with 32 pigeons, and they're all lice-free at baseline. So baseline, the word baseline means time equal to 0. Its baseline is a point in time, and it's nothing to do with values. It's got to do with time. The pigeons are of 2 breeds. There are large ones and small ones. The large ones are called giant runts, and the small ones are feral pigeons. Those are the regular sorts of pigeons that you see, wild pigeons. The giant runts are by weight 3 or 4 times as big as the feral pigeons. But more important than the weight is the structure of the barbs on the feathers, which are coarser. And that is what's supposedly going to introduce this differential evolution of the lice size on the pigeons. It's got to do with the barbs, or the coarseness of the feathers. There are the pigeons, these are all, so these feral pigeons have been captured, and so I call them feral, but bear in mind that they're in captivity. They're not flying around in the wild. They're housed in aviaries, and there are 4 pigeons per aviary, and each aviary contains 4 pigeons of the same type, either 4 giant runts or 4 ferals. They're not mixed. Now, at baseline, what happens? So what happens at baseline? First of all, the pigeons are cleaned, meaning any lice on them are removed. And how that's done is interesting in its own way, but not relevant for the, not important for this talk. And 800 lice were gathered from these feral pigeons or other feral pigeons, and they were partitioned up into 32 lineages, 32 groups of 25 lice each. So you can imagine, you know, got little jars of 25 lice in every jar, and then at baseline, these lice are attached to the pigeons, introduced to the pigeons, and then they live and breed on the pigeons for the lifetime of the pigeon. What happens after that is not entirely clear. Well, it is clear, but I'm not going to go into it. There are measurements made at 9 time points every 6 months from time 0 to time 48 months. So 4-year period. Measurements made on the lice. And the thought is that the lice on the big pigeons, the coarse feathered pigeons, ought to get bigger over time for various reasons that are explained in the paper. You don't have to buy the explanations, but that's what it is. And that on the feral pigeons, that they should either not change or maybe get whatever. But there will be a differential evolution over time from on the lice size. So we're measuring the lice size, and they should diverge over time. Okay, so that's the terminology that I am using here. We have got these 32 birds, 32 lineages. So lineage refers to a population of lice. There's one lineage on each bird. The lineage lives on the bird. And at every measurement time, 3 size measurements are made on a sample of lice. So the measurements are not made obviously on the pigeons, the measurements are made on the lice. So this is one of the things that I emphasize in here, which is actually one of the questions that flummoxes students who, I don't know, you ask them, what are the observational units? And they look at you like you've got horns, longhorn cows, you know, look like you've got horns coming out of your head. Because I'm talking about our own students. The students that here would be different, of course. They would know exactly what was meant. But what are the observational units here? The observational units refers to the things that are being measured. These are the lice at a given time. Now you should know also, it's relevant to this, that the lifetime of a louse, one louse generation is roughly 3 to 4 weeks. And the measurements are made every 6 months. So no 2 measurements will ever be made on the same louse. So there are many generations, roughly 60 generations of lice over this time period. And from over 6 months, you have got 8 or so lice generations. So you'll never be measuring the same lice more than once. You also should know that adult lice are sexually dimorphic. The females are about 18% bigger by linear dimension, longer than the males. Okay, so all of that information is relevant to the analysis and will come in various ways. So here's a schematic diagram of the randomization. I should say that most of the examples in this book have to do with experimental work, not all of them, but most of them. And so that means that there is a randomization stage and there's a treatment being assigned. Although very often the randomization aspect of things isn't emphasized in our methodological teaching, I'm afraid, but it's important for me, and it's important in this book, so I'm emphasizing it here. So this is just a schematic diagram of the randomization. now randomization doesn't mean random sampling. So random sampling is just forget it. It doesn't ever come up in scientific work that I've ever come across. It comes up in, where it comes up, current population sampling. You do random sampling there. Almost never comes up in scientific work. Randomization is a different matter. It means random assignment of treatment to something. At this stage, so we start off with 800 lice, and they're split into 32 lineages. That's the left-hand side, and I imagine that being done uniformly at random, not quite for various reasons, but roughly speaking, partitioned up into 32 lineages. And on the right-hand side, you have the 32 pigeons being split up into 8 aviaries, 4 pigeons per aviary. Again, that's not uniformly at random because each aviary contains 4 pigeons of the same breed. And the third part of the randomization is a permutation from 32 lineages to 32 pigeons, 1-to-1 correspondence, random. So this is an example of randomization. It's a 3-part randomization. The 3 parts don't all have to be done at the same time, and probably aren't done at the same time, but let's not go into that too much. Okay. It's always a good idea to look at a little bit at the data, just so you get an idea of what it looks like, how. And of course, you can look at numbers, you can select the various numbers here. I should say there's about 3,000 measurements here altogether. I'm only looking at lice length, just one observation at one measurement at each time. I'm not looking at the other 2, which are head width and metathorax width. Just looking at the length, and just looking at length, there are about 3,100 observations. And what I've done here is just look at the average size by sex and by host at each time. And as always in applied statistics, when you're dealing with positive measurements, you always take logs. And that goes without saying. It's not that it makes a big difference here, but there are various reasons for taking logs that have got nothing to do with adequacy of the fit of the model, that have to do with the interpretation of coefficients, as we will see later. The thing to notice about this is there's very little variation. The variation is extraordinarily small. Now, I should say these lice are about 2.5 millimeters in length. And this is the log of the length in micrometers. And so all of the numbers are about 7.8 for females and 7.7 for males on the log scale. And the differences, I've shown you the differences down here at the bottom, and I've multiplied them by 100. So remember, I've taken logs. There's very little variation, very small variation, I should say. And now I've taken the differences and I've multiplied them by 100. And that's one of the nice things about logs. When you multiply them by 100, these are just percent changes. So these numbers at the bottom are just percent differences. And they differences of the size of the lice on the giant runts minus the feral. And there are the numbers there in percents. You can see that the changes are not big on the whole. They're not all positive, but mostly positive. And well, make of that what you like, but let's continue. So we've learned something about the size of the variation. It's not big, and so on. You can plot the data too. That's always a good thing to do. And here are the plots of the body length, again, all on the log scale again. And I've shown the head width and the metathorax width. And there's something called PC1, which is a first principal component, which is basically an average of the three body measurements over time. And the question of genetic interest here in terms of speciation has to do with the question, are these lines diverging in a systematic way, in a statistically significant way, whatever way you want to put that? Is this divergence more than would be expected on the basis of randomness alone? Whatever that means. I don't mean, when I phrase these questions, it may sound like I'm phrasing it as a significance testing question. I don't necessarily mean it that way. I mean it anything that would purport to give an answer to that sort of question. Okay, so I've already talked about some of the terminology that I'm using here, but it's a good idea at the very big outset to do a deconstruction of the design in terms of what everything means. And I'm using the various terms in blue here. The definitions are exactly as recorded in this piece of paper here. An observational unit is a louse at a particular time. The time, yes, there's a time which here is going to be measured in months. Every louse belongs to a lineage, and so lineage is a block factor that has 32 blocks. So every bird resides in an aviary, and so aviary is a block factor, splitting the birds into 8 blocks of 4. Each bird has a breed, which is either giant runt or feral, so host or breed is a classification factor for birds. So lineage is associated with birds by 1-to-1 random permutation. So host is the treatment factor here. The breed of the bird, the coarseness of the feathers, if you like, is the treatment factor for lineages. Lineage is the experimental unit. It's very important to understand that an observational unit and an experimental unit are very, very different things. The experimental units are the things that the treatment is applied to. The observational unit are the things that the measurements are made on, and they're very, very different things here. The lineage is the experimental unit here. The observational unit are the lice. So it's very easy to understand what a sample is, just a set of things. And we use the word a lot in statistics, and it's one of the things that I have learned over the years is that I can use the word sample, and you may probably hear random sample, but that's not what I'm saying, and it's not what I mean. And when I say sample, I just mean set. I don't mean random subset of anything. So just bear that in mind. We also use the word population. We are all aware that the sample and the population are not the same thing. But we very rarely say explicitly in any text what the population is. So when you ask somebody what the population is, well, whatever it is. I'm at least in this book, I insist on saying what the population is. Population is everything. So the populations are, at least in my world, where I'm not concerned with current population sampling or political sampling or anything like that. I'm concerned with scientific work. The populations are always infinite. So there's an infinite number of observational units and an infinite number of experimental units. Bear that in mind. The covariate in this case the only covariate here is time. Treatment is for reasons that are maybe not so important, but they're technically important. It's not a covariate, it just occurs, the treatment is, the randomization is established at baseline. randomization values are just after baseline. And so technically in my world, treatment is a post-baseline variable and not the same as a covariate. There's a complication here having to do with the sex of each louse. Most of the sex of the lice sex, most of the lice that are measured are post-baseline, and their sex is not measured at not recorded at baseline. So that's a post-baseline variable. It's not a covariate. But for various reasons, it's going to be treated as a covariate. And we have aviary and lineage as block factors. So that's the terminology that I'm going to use here. And okay. Now, let's move on to analysis things maybe that are more familiar to students and faculty and in linear models. So when I write down a linear model, I'm just going to write it down as they're all going to be Gaussian models. So I'm not going to consider any generalized linear models today. And when I talk about a Gaussian model, it's just going to be a matter of saying what the mean is and what the covariance is. That's it. Not quite it, but that's near enough it. At least for likelihood analysis, that's it. So here's a model for the expected values. Now, the expected values are going to depend on the sex, obviously, because we know that the males are, 18 or 17% smaller than the females. And what else do we have? We have the treatment factor, which is host, and then we have time. So the first model here says it's just a linear combination of host, sex, and time. H is the treatment factor, S is the sex, and T is time. And then in the second model, H1, I have different slopes for the two hosts. So basically, the first model says that there's no divergence taking place, but they're both drifting off at the same rate in some direction. And the second one is saying that the slopes over time are different. And the focus here for differential evolution, these things diverging, has to do with the differences between the beta for the giant runts and the beta for the feral pigeons. So that's the second one. And you can express those factorial, I'll call those factorial subspaces. You can express them in usual model formula notation. The first one is dimension 4 and the second one has dimension 5. And then there's a model for the covariances, which is just a standard block factor model, which is just the identity. The first one is the identity. The second one is a block factor for lineages, so there might be some correlation for observations on the same lineage. Well, you would certainly expect that. That's in the nature of things. And then maybe for aviaries. So L in the delta here, what am I talking about here? The L's here, this is lineages and this is aviary. So when I say that something is a block factor, I'm talking about this block matrix here. Just says it's 1 if the two observations come from the same aviary and 0 otherwise. And this one is 1, this is a matrix, which is 1 if the two observations, the two units, I should say, come from the same lineage or different lineages. 0 if they're from different lineages, and this one is just the identity matrix. So these are just three different versions of the identity matrix expanded out. Okay, and then getting back to the paper, this is the model on which all of the conclusions in the paper are based. So the focus is on the differential evolution, beta for the giant runts minus beta for the feral pigeons. And I put up a rhetorical question: is this model a reasonable place to start? Well, certainly if you come through most statistics courses, you'd probably think it's a fairly reasonable place to start. But I want you to think about that for the next 5 minutes, because you wouldn't be here if the answer was yes. Okay. But I will just show you what the output from that looks like. This is something that makes my skin crawl a little bit to see computer output on a screen like this, because there's most of what you see here is really not very important. But I will just, I suppose, say a little bit about it. This is which one is it? I'm going to be talking about two different computer packages. One of them called regress and the other LMER, and basically they give you identical outputs in settings where they are both applicable, which is here, where they would both work. And the formula here is the syntax here is the syntax for LMER, and it just says the first part is the linear model part, the mean, and then this second bit here says that you have got a block factor for aviary and an extra term for lineage, meaning independent and identically components for each lineage that are constant, except for lineages. And the output for that looks like, well, you see it here. There are 3,098 observations, the 32 lineages, 8 aviaries, and so on. And the focus here is on the difference between these two regression coefficients. And the value here, you can see it is 3.5, 10 to the minus 4, standard error, and so on. And if you're thinking of publishing your paper, you're probably going to be looking at this number here. Is this number bigger than 1.96 or not? Because that's quite important for publication. And you reassure yourself that here this definitely is bigger than 1.96, and we're in good shape. Okay. Now, one of the things that I try to emphasize to my students, most of whom are coming with a mathematical background, is that everything in a computer output has units attached to it. And so just to tell me that this number is 35. I put it 10 to the minus 5 there, 35.2, 10 to the minus 5. Tell me what it means. And so, and this is one of the reasons that I've taken logs here, because this 35.25 by 10 to the minus 5 is on, remember, it's per unit of time. It's something per unit of time. Time happens to be measured in months here, which is why this number is so small. And 35.25 by 10 to the minus 5 per month is 4.23% per decade. So, if you express it that way, it's a percent change per decade. It sort of begins to mean something. That's the percent change in size per decade as these two, as these lineages evolve. Now, the experiment only lasted for 4 years, so it's not well, of course, you can look at that in various ways. 4% per decade doesn't sound that much, but for an evolutionary biologist, this is enormous. They bear that in mind. And maybe so enormous that it's not really credible. I'm not an evolutionary biologist, so I don't have any credibility in that sense of talking about what is credible. But there's a difficulty with this model. It doesn't conform with the randomization. It's in conflict with the randomization. And when I asked the question, is this a model a reasonable place to start? There are several reasons why it's not a reasonable place to start. And I'm going to go through them. There are at least 3 reasons that this is not a reasonable place to start an analysis. And when I say it's not a reasonable place to start an analysis, I mean that you have enough information at your fingertips. You have enough. I've given you enough information that you should know that this is not a good place to start. And I'm going to tell you why, for at least 3 reasons this is not a good place to start. And one of them is that under the randomization that I told you about, all of the, there's complete exchangeability of all the lice at time 0. So just think about what that model implies at time 0. There's complete exchangeability of all the lineages at time 0, and therefore there should be no systematic differences of any sort at time 0. So in either of these models, either of these expectation models, there should be no host effect because they're assigned at random to all. There's no host effect, and that implies that the beta 1 there must be 0. So we already know that beta 1 is not. So there's no point in putting in a beta. Now you can go back and look at the coefficients that I showed you there and just see, well, was beta 1 0? I didn't look too closely, probably nobody thought to look too closely. And you can see that the giant runt variable here, it's only 0.3 of a standard deviation. So indeed it is consistent with 0. Shouldn't have been there in the first place, but maybe it's not doing too much harm. So this notion, how to say it, of this issue about conformity with baseline is an issue that comes up in applied statistics for a very long time, and I've given you 2 references there, one from Eden and Fisher in 1927, and basically it means in Eden and Fisher's case, they noticed that a 0 dose of one fertilizer was exactly the same as 0 dose of another fertilizer. But you couldn't tell which fertilizer wasn't applied to a particular. If no fertilizer was applied, you couldn't say whether it was 0 amount of A or 0 amount of B. They're the same. And that's what's going on here, that the treatment here has a dose level, which is time. Think about it formally. And then in the example from the generalized linear models book, exactly the same thing comes up in one of the first exercises. So this issue's around for a long time. Now this turns out to be the least important issue in this case, but it's there and it's easy enough to take care of. You just you leave out the host and do the analysis again, and you find that the estimate comes out to be probably got my powers of 10 different now, but it's instead of being 35.25, it's 13.7, so it's come down by a factor of 3. But mercifully, the T ratio is still above the magic level. So we're still in good shape. We can go ahead with publication, even with that correction. But I raise my hand again, but there's another problem, which is that the block factor model is also in conflict with randomization. Block factor model says that these covariances depend on the lineage and the aviary, whereas the exchangeability at baseline says that there is no difference in variation associated with aviary at baseline. There's no difference in covariance associated with aviary or with lineages. So so that implies that sigma 1 squared equal to sigma 2 squared equal to 0. It's the only submodel that's in conformity with randomization at baseline. Now, I'm not saying that these should be, anyway, come to that in a moment. Now, you can correct it, you can correct this model in the same way as we corrected the other one by going to the submodel. Submodel says leave out the block factors. The trouble with that is that if you look at the likelihood function, the likelihood function drops drastically. It drops, I don't recall exactly the numbers. I have done the calculations. I had noted them somewhere, but anyway, I don't have the figure at hand, but it's on the order of, in the twice log likelihood scale, it's on the order of 50. So it's huge on 2 degrees of freedom. It's huge. It doesn't matter whether you're a Bayesian and would prefer a Bayes factor or whatever. it's just astronomically unsatisfactory. So in other words, the only model that's compatible with the randomization is just a bad fit. And the model that we have here is not compatible. It gives a better fit, but it's not compatible with randomization. So we're stuck on the horns of a longhorn here. Where do we go? And I'm going to have to speed up a little bit. I'm going to change gears now and say a little bit about Brownian motion. So most of you here know what Brownian motion is. It's just a Gaussian process. And it's starting off at time 0, it's equal to 0, and the covariance is just the minimum of the 2 time points. And the increments are independent stationary Gaussian increments. That's all there is to it. And we can put in a drift if we need to, and we can change the volatility, but I'm not going to do that. So why am I talking about Brownian motion? Why have I switched gears so completely? Well, it's for a very simple reason that this Brownian motion comes into evolutionary genetics. It's a standard thing in evolutionary genetics. It goes back to Cavalli, Sforza, and Edwards in 1967. So it's been around for 50 years, more than 50 years. And it basically says that a population, that for the evolution of a quantitative trait, now specifically for quantitative traits, the notion is that most quantitative traits are governed by a large number of loci on the genome, and that every locus contributes a small amount to the overall, whatever it is, height, size, length, quantitative trait, and that as mutations build up in different subgroups or whatever, they each mutation contributes a little bit to the quantitative trait, and independently for every locus, if you like. And that's the way you build up Brownian motion. That's where Brownian motion comes from, large numbers of independent contributions from these loci as they evolve. So the notion here is that in this setting, we're looking at the evolution of lineages. We're not looking at the evolution of lice now, we're looking at the evolution of lineages. And so each lineage evolves as a Brownian motion, but lineage isn't the only object that's our interest here. Each aviary can also evolve, and so on. So you can then have a covariance that looks like this. That instead of having, here we have lineage, the identity function of lineage, but we've also multiplied it by the minimum of the 2 time points. So this expression here just means a Brownian motion associated with each lineage, and this just means a Brownian motion associated with each aviary. And that's what it looks like. I'm going the wrong direction. So here's a Gaussian model that's compatible with randomization. The expectations are the same as before, and instead of having the covariances here, I put in an overall Brownian motion, one associated with lineages and one associated with aviaries. Three variance components plus the identity here, so 4 variances. And showing you here how to do the calculations is just the minimum of the 2 time points, and this is the minimum of the 2 time points multiplied by the block factor, and that's a Hadamard or component-wise product. I'm going the wrong direction here. And how do you do the fitting for that? Well, the first one here I've switched over to the other function, regress. The regress has a different syntax. You put in the expectation. There's 2 model formula, one for the expectation and one for the variances. This is the block factor model. And this is what we've already seen before. And if you want to use the Brownian motion model, you have to set up these matrices, and you just do the same expression is the same. And here we're focusing on the differential evolution, the differential slope over time, and the value has gone down. So the value is 1.37 here, gone down by a factor of 3 for the slope. But more drastic than that, what has happened is that the standard deviation has gone up by a factor of 10. Now, for a standard deviation to go up by a factor of 10 is astronomical. And astronomical, for an estimate to go down by, the value itself to go down by a factor of 3 is something, but it's not huge. The big difference here is in the standard error. And I've just shown here what the difference in log likelihoods is. 115. So there's a huge difference, improvement in log likelihood from using this Brownian motion. No, I'm not claiming any of this. All of this is standard in the literature, in genetics. It just wasn't used in this paper. I don't have time to go through likelihood ratios because they're a bit more complicated, but they confirm. I'm going to leave that out. So now I've shown you how to get a Gaussian model that's in conformity with random. The difficulty is from a consulting point of view, you've told the client, look, there's nothing there. It's just totally just random variation. So the apparently significant effect that you got is purely a consequence of using an inappropriate model. You left out the critical term, which is Brownian motion, and there's essentially no serial correlation in any of this other than the constancy of the block factor, which has negligible effect on things for various reasons. Now you can ask, well, how do I know that the Gaussian model that I've shown, this Brownian motion model, how do I know that that's a good model? Well, it's one of the difficulties of applied statistics is it's very hard to know that. You have to look at the data, and here I'm looking at the data in another way to see if it's in reasonable conformity with the model. So here I'm looking at the trends in mean squares and variances, and I've multiplied everything by 10 to the 5, just so that they're on a reasonable scale. And you can, but it doesn't really help to say just look at these numbers. I'm going to have to point out some things to look at. There's a lot of numbers here, and what should I be looking for is part of the question. Well, first of all, I'm looking at the baseline mean squares. Are they in conformity with randomization? I assumed that they would be. I assumed that the randomization was as I described it, but actually it's not quite. So these numbers are mean squares, so they should all have the same expectation as the residual. And well, you might think, well, this 12 here looks very small compared with the residual. It's not actually. It's only on 1 degree of freedom, and it's not particularly small in the usual sense. This number 290, well, that looks a bit big, does it? Actually, it is a bit big. It's on 6 degrees of freedom associated with aviary, and it is a bit on the big side. It's not hugely on the big side. It's not enough to convict anybody in the court, but it's enough to just maybe put a question mark beside it. So yeah, and lineage here, 83 versus 111 is more or less spot on. Okay, so that's the first. But now, what else should we look at? The stability of these residual variances. Well, these are the residual variances at each time, and these are remarkably stable except for the first one. The first one is about twice as big. Well, that's very unlikely to happen. So the model is not actually a good fit. It needs an extra boost to increase the baseline variability. Okay, and we can deal with that. And the other thing that the model says that there should be increasing temporal trends in these variances over time. And you can look at that and say, well, scratch it in. Doesn't look very convincing, does it? Okay. And this one doesn't look very convincing either. But it's not such a big deal. The main thing is the baseline variability needs to be increased. Well, there's another aspect of things that I should point out here, that if these sample size calculation that I'm going to refer to had been done before the experiment was proposed, the experiment would never have been carried out. There just isn't enough power in the experiment to detect anything that's likely to be detected. If you set up, and this is a simplified version of things, just a simple Brownian motion admixture regression. And what is the variance of the beta hat as a function of these two variance components? Well, if the Brownian mixture is absent, the variance is this. Here I'm taking the time points equally spaced. The variance will be that. That's 1 over the sum of the squares of the t's. If it's all Brownian motion, the variance is 1 over n minus 1, exactly. And the question is, what about these intermediate points? Well, it turns out that these are the values. So basically, if you have a tiniest little bit of Brownian motion admixture in the model, even a very small fraction, that will dominate the variance of the regression coefficient. So instead of having a variance of order 1 over, well, as it's done here, 1 over n cubed, you have a variance of 1 over n. So it's 2 factors, 2 orders of magnitude difference in the rate of convergence. Okay, so that's so I said, if this sample size calculation had been done in advance, the experiment would never have been carried out with that sort of size of. Of course, getting to this calculation, you need to know something about the parameters. So if you want to, I'm going to have to go through this, yes, yeah. And if you want to read, if you want to learn more about it, you're going to have to go to the book, I'm afraid. I'm not selling it, but this is it, it exists. And there are other issues that I haven't gone over here. They're all discussed in the book. And it shows you, this is one of my favorite examples in the book. It's quite a rich example, as you see. From a methodological point of view, you can learn a lot. You learn a lot about a lot of things, about lice, about pigeons, about random effects, about Brownian motion, about sample size calculations and so on, about terms, statistical terms. Okay, and I will, and if you want this regress function, you can get it there. And you can check it out in the book. Okay, well, thank you.
We're pretty much out of time, so there's a question. There is time for maybe one question. Yes.
So the data that you had is naturally longitudinal data in the standard term, and to assess temporal dependence, you can go through Brownian motion, plot the raw data. But did you do any plotting of the raw data over the equally space time to see what kind of?
The first plots I showed you were of averages over time for the two groups. There were 4 plots there, one for length, one for metathorax width, one for head width, and one for principal. Yeah, so the plots over time for sure, yes.
Brownian motion type behavior.
Brownian, that's why I was looking at those variances over time. The effect is very small over a 4. Things don't happen in evolutionary terms. You don't see much over 4 years. So a Brownian drift over 4 years, You're not going to see much. And the answer is, that's my answer. You don't see much. It's the Brownian motion, in terms of the model, the Brownian motion is definitely there in terms of likelihood calculations. There's absolutely no doubt about it. So there's correlation over time, yes, but you're not going to see much in plots.
Thank you, Peter. Let's conclude this